This is a Math 2 summary video for the lesson titled Symmetries of Regular Polygons. This is a solidify understanding task. The purpose of this lesson is for students to find lines of symmetry and centers and angles of rotational symmetry that carry a regular polygon onto itself. A line that reflects a figure onto itself is called a line of symmetry. A figure that can be carried onto itself by a rotation is said to have rotational symmetry. A diagonal of a polygon is a line segment that connects consecutive vertices of a polygon. For each of the following regular polygons, describe the rotations and reflections that carry it onto itself. Be as specific as possible in your descriptions, such as specifying the angle of rotation. A regular polygon is a polygon that has sides that are equal length and angles that have an equal measure. So an equilateral triangle and a square are regular polygons. Let's start by looking at the equilateral triangle, and we'll look for reflections that carry the figure onto itself. So I'm going to use patty paper, this transparent paper, so that way I can fold it. And if I want the triangle to line up with itself, I start by trying to just fold it in half. So I can fold this triangle in half and it lands on itself. And when I say in half, I mean I'm connecting a vertex to a midpoint. So this is a line of reflection. And I do know that lines of reflections are perpendicular bisectors of segments. So this is the perpendicular bisector of this segment. So of the base of my triangle here. So that is one line of reflection. I also know that this is an equilateral triangle, so I could look at it from this angle. So this perpendicular bisector of this segment is a line of reflection that carries it onto itself. And I could think of this also as this segment. So I have a line of reflection over here. So any of these three perpendicular bisectors of the side lengths would be lines of reflection. Now let's take a look at rotational symmetry. With my equilateral triangle, if I rotate, here the figure has rotated onto itself. I'm going to continue rotating and see here the figure has still continued to rotate on itself, and then I'm going to continue to rotate and I'm back to where I started from. So I did a total of 3 rotations. So when going around 360 degrees, there was 3 times where the figure landed on itself. So 360 degrees total. So in a full circle, there were 3 times that the figure landed on itself, meaning that I can rotate 120 degrees to get this equilateral triangle to land on itself. So let's try that out just one more time. So I rotate once, twice, 3 times, and I am back to where I started from. So each one of those rotations must be 120 degrees. Now to find the center of rotation, which is also important, I have a point right here that looks like it's probably the center. Let me try it out. So there's one rotation of 120 degrees, and the figure does land on itself. Second rotation, and the third rotation to get back to where I started from. So my center of rotation is the intersection point of my perpendicular bisectors of the sides. So let's summarize this information that we've learned about the equilateral triangle. So what I'm noticing so far is that this regular polygon had 3 sides. It had 3 lines of reflection. And to find the angle of rotation, I took 360 and divided by that same 3 to find the angle of rotation. My next question to myself would be then to ask, does this always happen? Do the number of sides always match the number of lines of reflection? Can I take the number of sides and divide it into 360 to see if I get the angle of rotation? Try experimenting with these other polygons to see if the relationship holds true. That's it for this video. Thank you for watching.